Lab 27, Redox Titration.
Perfect. See, and that's a nice drop rate. It's really nice slow. So you should be able to stop it. Ozzy. When I did it, because I was trying not to get my hand in the camera, and it was a mess. So that is perfect. Good job. Bailey's gonna be a pharmacist. She's got it down.
So, change your.
Nice job.
No, dude.
Nice job. Really nicely done.
Change this to 23.4 because the intermediate.
Go to Alaska.
You won't get drafted into
No, that's just want to tax you.
Alaska. We're gonna run out before you.
We have plenty of
Well, I'm doing Mon Capitan.
They're lasting a little longer. They're starting to last a little longer, then they're getting closer.
Mom,
What?
no. What's this level called again?
Stop cock.
Stop.
Yeah, I know you
Although I
wanted me
would
to
be
say that.
afraid
You
to
just
live
wanted
there
me to
because
say it.
problem
I
is-
know. That's getting closer and closer. That's good. Look at that. Ooh, it's almost there. Look at that.
I'll knock it down 2 inches.
How long have you had a Aussie for?
Oh, a little over a year. We got it last January, so. So pretty. Look at that.
I was just like, huh? Just touching my head.
Are you doing the...
One moment.
Patience, patience.
Oh, okay.
Titrations teach you patience, if nothing else, right?
The only thing that took me patience was drawing.
Oh, yeah.
Nothing else to learn. Made me
Almost
learn
there.
patience.
The longer that lasts, the better it is. Closer, closer, closer. Look at that. Getting there. Almost got it.
Cricket fighting.
Oh yeah, in China, cricket fighting? I've seen that. Well, I saw them doing it, but I didn't want to watch because it sounded brutal. So, ooh, 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 watch.
Do crickets fight?
Look at that! That was perfect. That is spot on, girls. Spot on.
Okay guys, we're going to go over our data from today using the averages we acquired from the 4 teams present in lab. Keep in mind this data is going to be different from the data that I put out in the lab video for the cyber rats and anybody who was absent, because I did intentionally use a different molarity for our unknown solution. So if you were in class today, this should help explain your data. So here are our figures from today. So these are our averages, and the delta would be the average volume used between the initial and final readings. So our first question says, calculate the number of moles of NMO4 negative reduced in each trial. So we're going to go about that first by considering how we look at molarity. We look at molarity at moles per liter. So 1 milliliter is 0.001 liters, and therefore MnO4 negative, there should be a negative there, sorry, MnO4 negative, our molarity was 0.02 molar, which is moles per liter, which means that it is 0.00002 moles per milliliter, and we were working in milliliters. So for our first trial, we're going to take our average results, and we're going to come up with how many moles we consumed. That's how many moles were reduced in trial 1 on average. For trial 2, we get this figure for our number of moles reduced on average. And for trial 3, so we did this by using the moles per liter and the known volume in milliliters and the known molarity, which was moles per liter, converted into milliliters since that's what we were working with for volume. All right, so now we're going to take that data that we just got and we're going to analyze it by calculating the number of moles of Fe2 plus oxidized in each trial. All right, so here's where we need to look at our equation and we need to do a half reaction. So we need to consider our oxidation numbers, and here they are. So we know that the iron is losing electrons, so it's oxidizing, and we know that it's losing electrons because it goes from a +2 to a +3, which means it is less negative. So it is losing ions and it is oxidizing. And losing electrons and oxidizing. And our manganese is gaining electrons, it is reducing. That is because it goes from a +7 to a +2. So here we go, we're going to take our iron, that's a half reaction. Here's our other half reaction. All right, so now we're going to take these two sets of numbers and we have to consider what the change was. And the change here, since we're trying to work with the Fe2+, the change here is that we lost 5 electrons. So we have to take the other side and multiply it by 5. So that looks like this. We're going to balance the equation and multiply them both with a coefficient of 5 where that ion is concerned. So we're going to take our balanced equation now. And here it is. And then we can go to our next step, take this data that we currently have and our equation that we've now balanced. So now that we have this equation done, we can figure out how many moles were oxidized. And we do that by working with the figures we have here, our 5 moles to 1 mole ratio, and we calculate out to 0.00014 moles. That is because we have 5 here, so we're working with the 5. Basically our coefficients are 5 and 1, so that's our ratio. So our ratio needs to stay 5 and 1. All right, and here we go for 2. And again, obviously 3. So these are pretty consistent numbers. This is looking good. So we're going to take all that data that we have now, and now we get to calculate the molarity, which is our moles per liter. So what we did to calculate the molarity here is we took what we had, which was moles per milliliter, multiplied it by 1,000 to get it back into liters. And then we can take that molarity of moles per liter here and add up the 3, divide by 3, and we're going to come up with an average molarity. So you see what we did here, we took the numbers that we had just come up with. Here's the MnO4 negative, Fe2 plus, these are our 3 trials. We're going to take this is moles, and we were dealing with milliliters, so we need to take it back and make it moles per liter. Here's our moles per liter, which is our molarity, right? That's our molarity number. So here's what we got, 0.147 moles per liter. So explain the events. Can you explain here, why is it so important to rinse the burettes with the potassium permanganate and the iron 2 sulfate before adding the solutions? So we can see pretty clearly why that was necessary. The concentrations and volumes are so small that even a drop of water could cause the results to be way off base. Even one extra drop of potassium permanganate could cause you to overshoot a titration, as many of you saw. So we have to make sure that we have no excess water in any of the burettes, and we have no bubbles, we have no contaminants of any kind. Okay, so here's where we put our data into context. The company makes 3 different types of iron tonics. Sphaervide A with a strength of 0.145 molar iron 2 sulfate, Sphaervide extra strength that is 0.225 molar iron 2 sulfate in Ferrified Junior, which is 0.12 molar iron 2 sulfate. So which tonic is your sample? Well, based on our data, we had the average result of 0.147 molar iron 2 sulfate. So we can pretty much assume that's going to be right here. Look at how close that was. And this is straight from the teacher's manual. So I have prepared a 0.15 molar, and you guys had a 0.147. And this is from the lab manual as a 0.145. So they had left some room in here for error, but you guys were so stinking close. That is outstanding. You were actually even closer than the example the book gave. Really good.